that somebody has brought something for me. Yeah. So I can write down the equation quite straightforward. So let us write it down. So I have first minus half Laplacian chi I. Note that if I am going to do this, sum over I, if I differentiate in specific chi I, again the same thing will happen. The sum will vanish, one chi I will remain. I am differentiating in respect to chi I star. It doesn't matter. The rest will be conjugate. So I get my first equation just like in Hartree form. Then the second equation is V of R, del L, del rho V of R, and each time I am going to multiply chi I. The second equation in terms of rho was very simple. It was only V of R, but now it is respect to chi, so I have to multiply del rho del chi star, so I get chi I, right? And then I have the Coulomb term, just like here. Now you can keep doing it. So I had this derivative, which was integral, if you remember, integral rho of R2, 1 by R minus R, dRP. Please remember that half plus half I told already. If I differentiate, what will happen? So we have this again times chi I plus the derivative of the exchange correlation potential, which is now the Vxc of rho into chi I. Chi I, of course, yeah, I should write this as a not R but X. The spin orbital. Equal to sum over j lambda ij chi j of x. I hope this can be trivially integrated. If you are differentiated, if you differentiate this again with respect to chi I star, this integral differentiation and integration only chi j will remain. This sum over I will go lambda ij chi j. So actually DFT has a lot of calculus. It's very important to understand calculus. So every time you have to do differentiation under integration. Okay? So but that's what you will get. And if you now notice, this is just like Hartree-Fock equation. Except this is a non-canonical Hartree-Fock equation. And you can do exactly the unitary transformation to make it canonical. So this is, the Fock operator has only changed now. The Fock operator has now changed. If you again notice, everything else is same. You can expand this row in terms of chi I star chi I. Then you will exactly get the Hartree-Fock like equation. So there is no difference except this part. So this is new. So other than that, you have the kinetic energy. So everything can be written as a new operator. Let me call it Fkx times rho of R equal to epsilon I rho of R. And this I am doing without any further introduction, that I have gone into what is called now canonical Kohn-Sham equation. Note that the canonical is only to make this matrix diagonal. Now this is again mathematics, I will not go into it. One can show that this lambda is matrix is Hermitian first. Second is that if it is a Hermitian matrix, you can always find a unitary transformation to diagonalize. So I do a unitary transformation of these orbitals. Then I can show that the operator which multiplies the chi is actually Hermitian. So they remain invariant. So chi becomes chi I prime. The lambda is it becomes canonical. Only diagonal part remains. And sorry, this is chi I. So everything is now in terms of orbital. Sorry, I wrote down rho. That's not right. So just like in Hartree-Fock, I have an orbital equation. I get a canonical Kohn-Sham. And then you know how I solve the Hartree-Fock. F will depend also on rho, of course, quite clearly, all chi's. Chi's are stuck here. Remember, you can expand that. I didn't do that. And it can be done by self-consistent field. All the technology of Hartree-Fock will come. Except that this Fock operator, which is the one particle operator, is different. So this is where, depending on the functional, your exchange potential will be different. So that's why if you do B3 leap, you will get one kind of result. If you do LDA, you get another kind of result. If you do GGA of different kinds, you get different result. Because this is changing all the time. So this comes from EXC derivative. So this is changing all the time. And that changes the DFT. But in principle, the Kohn-Sham DFT has allowed you to write the kinetic energy term. And this now comes quite well. Because I'm actually having a Hartree-Fock kinetic energy, which is reasonably good. And provided I'm taking this exchange correlation potential correct, these orbitals actually give you a density which is exact. This is what Levy said. And this is what then goes back to Hohenbach-Kohn theorem. There's nothing wrong. So provided Hohenbach and Kohn said, energy is any function of density, except that I don't know it. But let's say you get up tomorrow morning and God tells you what is that function of. You have a dream tomorrow morning. You never know. If you have a right dream, and that's an exact functional, everything is okay. You get chi's which are coming apparently from non-interacting system, but the density is right. I'm not going to use these chi's. Chi's are no good for me, but the density is right. Provided you know the dx here. So everything now shoved into there. And in a very simple way, this works very beautifully. And better and better. The question is what is better? That is the whole thing in DFT. So that is the reason I said if you have a dream, tomorrow morning maybe, today you have missed it. So let's try tomorrow if you can get a good dream. What is the function of? You'll get it. You never know. You get everything right. Because Hohenbach and Kohn said there exists a function. Our problem is we are not able to derive. But provided we are able to derive, or somebody tells you this structure is okay. What have I done? I only avoided the kinetic energy problem. Because I had three problems. The kinetic energy problem, exchange, correlation. Exchange was somewhat okay. LDA is okay. GGA is okay. But suddenly correlation. But now at least I have bypassed the kinetic energy problem. Now my only remaining problem is X. X and C. X also I know dominantly X. C I know is not so significant. So something with bigger plane, all that I'm always extracting. So now the error that is happening is not so much. So that is why DFT works. If you apply Thomas Fermi, the error was terrible because kinetic energy was so bad. And kinetic energy, believe me, is a large part of the energy for every system. So that was very bad. So you don't get correct results. Now at least the errors are in decimals and people can play around. Though chemists are not happy because they want kilojoules per mole accuracy. Some of my chemist friends are smiling. They are not happy that the spectroscopy is such a resolution today that DFT has a problem still. But you see, look at that problem has been reduced to the Kohn-Sham approach. And after Kohn and Sham, this is 1981, I think, paper, the Kohn and Sham, and then DFT has become practicable because the Hartree-Fock technology was already available. So all we had to do is to shove this VXC of rho. And then people started talking of all functionals. So from 80s till today, you know, there are lots of, then people are looking at how do you do long range interaction, then non-bonding interaction, all kinds of things people are doing. And today one very big functionals have come, and I don't know how big they are. These are called Minnesota functionals. Many people have heard MO5, MO6, etc. By Don Truller, then there are so many. There are functionals which are taking care of these dispersion effects, which are very, very important in chemistry. So I mean, this we can keep on discussing. Right? This is not the forum probably to do that now. But the point is that this is making those fine print better. And those fine prints are important in chemistry. But you couldn't even do anything with Thomas Fermi because the kinetic energy was so bad. So basically we solve this canonical Kohn-Sham equation. Interestingly, just like Koopman's approximation in Hartree-Fock, this also have a meaning, although not the orbitals, the orbital energies. And by extended Koopman's theorem, the negative of the orbital energies for the HOMOs, occupied orbitals, are actually the ionization potential, and for the unoccupied ones, they are actually electronegative. So just like in Koopman's approximation. So that has been also shown. So that gives somewhat better feeling that the Kohn-Sham is even more practicable than what we thought. Because of this reason, that I also have a Koopman's right approximation. And I can get IP and EA. So there is something called the extended Koopman's theorem. However, I must caution that if you form a wave function with this Kohn-Sham orbital, this wave function probably has, so I call it psi ks. This probably has no meaning. First of all, as a single determinant, Hartree-Fock is always better. So this can't be better than the Hartree-Fock, because that I already know. So what good is this for a single determinant? We don't know. Because remember, when I did this formula went much beyond single determinant. If it was single determinant, I would not have correlation. I would have only that J minus K, that anti-symmetrized integral, right? But the formula I have used is much beyond single determinant, and I am assuming my wave function is single determinant. So the problem is, and this is a lot of people miss this. The problem is that if I write this is eventually not equal to psi ks, 8 psi ks. This is, I think I want to tell you plain and simple. Many people miss that. Why you miss that? Because you thought that I wrote E as a psi 8 psi. But that psi was exact psi. Now we are making a Kohn-Sham psi, which is single determinant. Because if it is single determinant, then C will never come. It is only J minus K, half chi j, anti-symmetrized chi j, remember? Only Coulomb minus exchange. So this I have already assumed exact wave function and then wrote. Then I am extracting the density from here. So I am only extracting density from here. That density is chi I star chi. But if I construct this Kohn-Sham, so-called Kohn-Sham determinant, and then try to calculate back this average value of Hamiltonian, it cannot be this. Very clear. Because that should have only J minus K, K coming from those orbitals, orbital exchange. But unfortunately, many people misunderstand this point. Many think that since this rho is exact, this is good, and then I can write that. No, that's not good. In fact, it is very clear that, that if you want to do, then E Hartree-Fock, which is psi Hartree-Fock, 8 psi Hartree-Fock, is at least better than this. Because that is lower than psi ks, 8 psi ks, by variation method. And I just want to say this because many people are confused. I have seen many experts even. Because they tell me, if by variation method this is lower, which this has to be lower, because this is variation principle. I have already applied for Hartree-Fock. Then how come this is DFT energy? How come DFT energy is lower than this? We always get DFT energy lower than Hartree-Fock because we have included correlation. The point is, DFT energy is this, not this. So this is not the DFT energy. Sorry. I only used the Kohn-Sham orbitals to construct kinetic energy. Then I have gone far beyond that. So that's why it is lower than Hartree-Fock. But many have started using psi Kohn-Sham as a starting reference function instead of Hartree-Fock. Then they do CI. Today people are doing CI using Kohn-Sham orbital. I don't see why. What is the point? Because if I do CI, I'd rather do Hartree-Fock. The reason is, if I do this, I'm already starting with a reference energy, which is worse than Hartree-Fock. Hartree-Fock is here. I'm already starting here. My total energy is here. Second, I don't have the Bredouin's theorem. Remember my Bredouin's theorem, occupied and virtual, 0. I don't have it. This is not varied. This is not varied with respect to this. This is varied with respect to this. And that's the difference. If you vary Hamiltonian average value with respect to single determinant, then you have a Bredouin's theorem. It's a very fine point I'm just telling you. And many have missed. Many told me, why don't you start with a cone sum determinant and do couple cluster? Yeah, it's a good idea. But why should I do it? Because in couple cluster, if I do start with Hartree Fock, the single excitation amplitude is small. Whereas now my singles will become very large because there is no Brillouin's theorem. So I have desisted from doing unless somebody convinces me to do. Why should I do it? I can easily do it. The couple cluster program is there and it's very easy to do. I have to get a paper also. Getting a paper is not a problem. Right? It's a good paper. If you do couple cluster, it's called something. Oh, paper will be published. It probably will go to a DFT referee who will be very happy. Oh, my cone sum orbitals are better. But not. The densities, however, are very good. Yeah, please understand. That's important. That is Leibniz.